So this is a series of slides about the rate of chemical change. So if we first look at some basics, we can think about rate being measured either by looking at the products being formed or by the reactants being lost. We can quantify this by measuring mass or volume before and after reactions occur. Hence, we can look at the rate of reaction being either the reactant lost over time or the product gained over time. And in later slides, we will look at how we can present this graphically, and we'll see that the shallower the gradient of a line on a graph, the slower the rate, and vice versa. A simple question on that topic is to calculate the average rate over 100 seconds, given that 20 grams of product is formed. So feel free to stop and have a go. So in terms of the answer, if we look at the info that we've been given, we know the time taken is 100 seconds and the product formed is 20 grams. So we can use the equation the product gained over the time taken. It's 20 over 100, so 0.2 grams per second. So if we look at the collecting gas or changing in mass or changing in concentration in terms of practical methods to measure rate, we can use a test tube in a water bath and seeing the water being displaced by the gas, or a more expensive and more accurate way, we can use a gas syringe. Mass change can be measured by scales, and concentration change can be measured by comparing the solute volume to the solution. So if we look at some graphs and maths, we can calculate the rate of reaction graphically by having time along the x-axis and reaction progress along the y-axis. So that if we take that as our curve, we can put a tangent at any point, and the gradient will be equal to the rate at this time. So obviously delta y over delta x. We can also calculate the mean rate of reaction by doing total reaction progress over time. So we can look at some reversible reactions. So we know that for this reaction to be at equilibrium, A and B rate of reaction must be the same as X and Z rate of reaction. So the forward reaction rate is equal to the backwards reaction rate, would be the simple way to put it. If we were to look at a graph showing this reaction of A plus B going to X plus Z, reaching its equilibrium, it could look like this. We can see that when the equilibrium is reached, the rates are the same. So if there are 4 main variables to look at that will affect rate. Number 1 is the temperature, then the concentration and pressure, the use of a catalyst, and surface area. So if we look at temperature, we know that when increasing temperature, the reactant's particles move more quickly and will have more energy. Because of this, a greater proportion of particles will have energy that is greater than or equal to the activation energy. This means more successful collisions will happen, which will result in reactions, meaning the rate will increase. So in a cold system, we could describe particles' movement as slow, and they will have infrequent collisions, and few of these collisions that actually do happen will result in a reaction due to the collisions not exceeding the activation energy. Therefore, we have a slower rate of reaction. In a hot system, particles have faster movement with more frequent collisions, with lots of collisions that do exceed the activation energy, so reactions actually happening when the collisions occur, therefore a faster rate of reaction. If we then look at concentration and pressure, which is, they go hand in hand through liquids and gases, and it's basically measuring the particles per volume, unit volume. So concentration is for solutions and pressure is for gases. If we increase the number of particles for each unit of volume, there's less space, so more collisions per unit time. So the rate will increase. So if we look at some examples of different concentrations on curves, we see that a higher concentration has a much steeper initial gradient and reaches the same point on a reaction progress graph faster than a lower concentration curve would, although the lower concentration curve is heading to the same point as the higher concentration one. So if we now look at the surface area as a variable, if we take three different sizes of breaking down the same mass, so these all have the same mass and volume, but have different surface areas because of how much we've broken them down. When breaking it down, you create more surface area, so there's more sites for reaction. So for the same proportion of particles that do come together and have a reaction, you're basically increasing the total amount of possible reactions. Looking at this quantitatively, comparing these different solids is easiest by looking at the surface area to volume ratio. The smaller the size of an object, the greater its surface area to volume ratio becomes. With a greater surface area to volume ratio, you're exposing more particles to be available as reaction sites, hence the rate increases. So then we'll look at the catalyst, the introduction of a catalyst. So we know catalysts do not affect the yield, but they will affect the rate. They reduce the activation energy by providing a lower energy alternative reaction pathway. We can visualize this using a graph. We see higher energy in the product, so we know this will be an endothermic reaction. So this would be the activation energy without a catalyst. And that'll be it with a catalyst. So you can see there is far less energy needed to go from reactants to products. So we know that catalysts do not change the products that are made in a reaction, so we don't have to show them in the balanced equation for a reaction. But we can write them above the reaction arrow, as shown here. Next, we'll take a look at particle theory. So for a reaction to happen, three parameters must be met. The particles have to come together, obviously. They have to have the minimum energy to react, which we call the activation energy. They also must have the correct orientation. Hence, to increase the likelihood of reactions happening, we can try and increase the frequency of collisions or increase the speed the particles are moving at, so increase the energies and try and increase the amount of particles that will have the activation energy. A type of catalyst is enzymes. They are biological catalysts. They are large proteins which are very efficient and work well at low temperatures. This means they're cost efficient when used in industry. Enzymes work by the lock and key hypothesis. We talk about them having an active site which will fit exactly to the targeted substrate molecule specifically, which we will think of as a lock and key. In terms of denaturing, this happens at extreme pH or temperatures. When an enzyme has denatured, it leads to the active site no longer fitting its specific substrate molecule. If we look at a diagram to show the lock and key hypothesis, we can see the enzyme and the substrate molecule, which fit perfectly together, like a lock and key.